All right, so this is the wrap up from the Force of Gravity Lab. Hopefully it wasn't too difficult. I may do this in 2 parts. Let's see how long it gets. All right. So the first part is, right, you're going to have your lab. All right, and you should have had FG up here and mass in kilograms here. All right. You get a nice line. It's a little bit, the data is usually pretty clean. All right. And then here I can see as the mass increases, the force of gravity increases also. All right. And the force of gravity, when we graphed it, right, or when we measured it, we had the force of tension on the mass from the spring scale, force of gravity on the mass from the earth. All right. And since the object was not moving, those 2 things are the same. All right. So we actually measured the force of tension. We can use it as force of gravity. Okay. All right, so when you write this, I think the number in the example was 9.9. Okay, that'll be newtons per kilogram times mass. Okay, oops, why does it keep doing that? How to get rid of that? All right, and oops, times, oh my gosh, mass. All right, this slope here says, right, for every 1 kilogram increase in mass, the force of gravity, okay, acting on the object, increases by 9.9 newtons. All right, and hopefully you recognize this, okay, as our good old friend, the acceleration due to gravity, around 10, 9.8 or 10, okay, and this is the same thing. All right, so when we're thinking about something that's dropping in free fall, we like to think of the acceleration due to gravity. But this here, okay, that's not a good color. All right, I like to think of as the gravitational field strength. Okay, all right, so we're going to call this the gravitational field strength. Okay, and it's about 9.8 newtons per kilogram, or often we can just use 10, again, newtons per kilogram. Okay, so every 1 kilogram of mass on the earth weighs 10 newtons. All right, this number would be different, okay, on the moon. It's about 1.6. Okay, also that would be its acceleration due to gravity. On Jupiter, I think it's about 27-ish, if I remember correctly. All right. All right, so this is showing you that the, not really the size, but the mass of the planet or the body is going to influence this pull. Okay, so all 2 masses, all right, exert this force of gravity on each other, all right, which just like our Newton's third law of pairs is equal and opposite. All right, so if I'm standing on the earth, okay, right, and say, let's just use, I don't know, let's just say, I don't know, whatever, something weighs, not a person, whatever, like, 500 newtons or whatever. Okay, if this person's or weight is 500 newtons down, that means that this person is pulling up on the earth with 500 newtons also. Okay, on the person from the earth, on the earth from the person. All right, the earth is so massive, though, that this force is like nothing to it, right? It doesn't even really cause any appreciable effect, and then we have all the different things interacting with the earth, okay? But since your mass is so small, or the tennis ball, or the whatever you're throwing is so small, that amount of force can appreciably affect its motion. All right, later we will learn the bigger equation for force of gravity, which is this one. This will be in unit 7, okay? And then basically this part here, like I think we talked about the other day, right? This universal gravitation constant times usually the mass of the earth and the radius of the earth, that's where we get this number, 10 newtons per kilogram, okay? All right, so when we're actually looking at this equation now, what we have is force of gravity equals, we usually say mg, which is mass, times the acceleration due to gravity, or the gravitational field strength, which we call little g. All right, so what this means is that when you want to have something in weight, but it gives it to you in mass, so say 5 kilograms, that's about 50 newtons. Okay, or if they said something was 100 newtons, you'd be able to back that up and know that that's about a mass of 10 kilograms. All right, So this is the important part now, because what we really are going to be focusing on most of the time when we're at least drawing the force diagrams is the force. So if it comes given as mass, you need to multiply by that acceleration due to gravity or gravitational field strength to get the force of gravity, okay? Notice I like to put the units this way because just because you're using this number does not mean the thing is actually in free fall, okay? So keep in mind that I like to think of this way as more of, I like to say a conversion factor, even though it's not really converting because it's not the same thing, right? Mass and weight are very different, as you'll read on the next page. But I like to think of it more like a conversion factor than an actual acceleration, because it's not necessarily accelerating, okay? It's just sort of a way to turn mass into weight, okay? There's a couple of other videos that might be interesting, okay? There's a video about free fall, which kind of shows a couple of objects that fall at the same rate, all right? Even though they are different masses. And then there's an interesting little video about Einstein's theory of gravity, which we don't really cover in this class, but it's kind of interesting, okay? The free fall thing, I'm going to try to remember to kind of discuss that at the beginning of next class because it's kind of important, okay? But go ahead and maybe just watch that video, all right? And I think hopefully that's it, okay? Mainly you just need to know this equation at this point.